One latency number hides two bottlenecks. Measure TTFT and TPOT to see whether long prompts or token generation are slowing your LLM. You'll see how to connect the pieces into a workflow that measures token timing and points to the right tuning lever. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Latency in LLMs often looks like one big slow number to users and a single P95 to engineers. That hides two different causes: the time until the model emits the first token and the pacing of tokens after that. If you split those phases, you get targeted fixes instead of guessing. The practical goal is straightforward. Measure time to first token and the per token pacing. Then map each trace to the right action. A useful dashboard should tell you whether to trim prompts or tune decoding, not just that things are slow. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we measure the time to first token, so we can split prefill from decode. This snippet measures TTFT from two captured timestamps. Teams often feel a stream is slow before they know whether the delay happened before generation or during generation. The code keeps only start and first token, then subtracts them to produce TTFT-MS in milliseconds. That mirrors the first measurement you want around a real LLM request. Request sent, first chunk received. The snippet shows how start and first token map to a single scalar called first token MS, or TTFT-MS, which isolates the prefill-facing part of the user weight. You will see first token MS printed, so you can compare different prompt sizes or client-side network setups without the decoding noise. That gives you the first token split, but it doesn't tell you how tokens flow after that. Next, we'll convert a stream of token timestamps into pacing metrics. This example turns stream token arrival times into TPOT and ITL. A response can start quickly and still feel sluggish if each later token arrives too slowly. The code uses token times from the same trace, builds ITL-MS between neighboring tokens, and averages those gaps into TPOT-MS with mean. Keeping the final gap visible is useful because a single stall can hide behind an acceptable average. The output shows the average token pace and the last gap, so decode behavior is no longer blended into TTFT. You can use TPOT-MS to monitor decoder stalls and ITL-MS to catch isolated hiccups that need retry logic or back pressure fixes. Now that we can measure both sides, we need a way to compare traces and name which phase each trace stresses. The next snippet does that. This snippet compares two traces and names the phase each one stresses. If a P95 chart only says slow, engineers may tune the wrong thing and make cost or reliability worse. The runs mapping keeps each case as a pair of TTFT-MS and TPOT-MS. Then Max selects the trace with the slowest first token and the trace with the slowest per token generation. The output shows which case points at prompt prefill work and which points at decode tuning. This gives a simple classification. One trace looks like a prefill problem, the other looks like a decode problem, and you can prioritize fixes by the size of the gap each trace exhibits. If you suspect long prompts are the cause, estimate how much trimming helps before you edit half your prompts. The next snippet converts token reductions into estimated MS saved on TTFT. This snippet estimates how much TTFT improves when prompt tokens are reduced. Long context often hurts the first token before the model has emitted anything, so trimming should be evaluated against the prefill side of the trace. The code uses prompt tokens before and after a cleanup. derives MS per prompt token from runs, and turns the token reduction into saved MS. Increasing the removed token count raises the estimated savings. Trimming less gives a smaller and usually safer change. The output shows saved first token MS, which ties a prompt edit to a first token lever and helps you decide whether the user visible benefit justifies the prompt engineering effort. Finally, we want a compact action recommendation for each slow trace. The last snippet writes that decision out so dashboards can trigger the right playbook. This example turns the measured split into an incident-style next action. A latency dashboard is more useful when it says which lever to try first, not just that a request was slow. The code sets simple SLO thresholds, loops through runs, and writes actions based on whether TTFT or TPOT is over budget. In a production system, those thresholds should come from your own SLOs and model mix, not from the toy values here. The output shows the distinct next actions and how many cases were checked, giving a compact baseline diagnosis. Applied to a real system, you would collect these traces across your main prompt templates and your highest volume model. The same saved first token MS estimate scales to batches of requests, so you can prioritize prompt edits by user impact. What this does in 3 lines. It separates the prefill weight from token pacing. Use it when you see non-trivial end-to-end latency and need a clear tuning direction. Remember one caveat. Averages hide single long stalls, so always inspect the last gap or a high percentile of ITLMS before deciding. If you want to improve this exact pipeline, tune the removed token count for your top 5 prompt templates, and measure saved first token MS across the traffic mix. That one focused experiment will tell you whether prompt trimming is cost-effective or if you should tune decoder batching and chunk sizes instead. If practical AI engineering helps, subscribe and watch the AI engineering videos.